Today I'm going to tell you how to understand all Lie algebras. Well, maybe that's not totally true, but we are going to go over the core idea that drives the structure for all Lie algebras. So let's look at a bit of an outline of what I mean here. And so let's start with the notion of a Lie group. So a Lie group is just a group that's also a smooth manifold. And so you can think about like matrices whose determinant is non-zero. That's kind of obviously a smooth manifold, and it's a group. And if you're scared of the word manifold, we really just mean a smooth surface. So the interesting thing about Lie groups is that they have algebraic properties because they are groups, and they've got analytic properties, so you can like do calculus on them because they are smooth surfaces. And then, well, what's the Lie algebra? Well, the Lie algebra is the tangent space of the Lie group at the identity. So if we've got a smooth surface, then we can look at a tangent plane, or more generally a tangent space. And, well, we might as well do that at the identity, which is maybe the most important element of the group. So here's a little picture of that going on right here. You might say, well, why would we want to do that? Well, it turns out that you can understand a lot of what's going on in the Lie group by studying the Lie algebra using the really powerful tools inside of linear algebra. And so, in fact, we can't only just do that, but we can break apart Lie algebras into their so-called semi-simple pieces. And it turns out that those pieces come from a fairly small list. Well, the list is actually infinitely long, but there are only a few families, and every algebra in one of these families behaves very, very similarly. And inside of all of these algebras, there is a common component. And that component is the simplest Lie algebra, SL2. And we'll see exactly what SL2 is in a minute. And if you can understand what's going on with SL2, then that's going to inform the structure of the whole Lie algebra. Okay, so just as a bit of a summary of what we've said so far, understanding the representations of SL2, we'll talk about what the representations are, but that's going to be the main goal of the video. So, understanding the representations of SL2 is the seed to understanding the whole subject. And so today we want to look at or explore all finite dimensional representations of the complex SL2. But before we do that, let's do a bit of a history lesson. So it all starts with Galois. So in 1832, he was studying finite groups and polynomial equations, very classical stuff. He died in a duel at 20, but his ideas changed mathematics forever, studying solvability through symmetry. Next up, we'll look at Sophus Lie. So in the 1870s, he was a Norwegian geometer who saw the same strategy could work for differential equations. But instead of a finite group, we needed a continuous group. So that would be rotations, scalings, and flows. And instead of the group itself, his breakthrough was to linearize, to look at the tangent space of the group at the identity. That's the Lie algebra. Everything we're looking at today will start here. And next up, we'll mention Killing from the 1880s. He classified all of the simple Lie algebras. So those were those building blocks I was talking about earlier. There are 4 infinite families and 5 exceptional algebras. But his proof had gaps. Then Cartan came onto the scene and filled in the gaps and developed the representation theory that we're going to be looking at today. And nowadays, Lie algebras are everywhere, from quantum mechanics, particle physics, and number theory. And all of it traced back to one idea, infinitesimal symmetry, and all of it starts computationally with SL2. And now what we're going to do is derive what the Lie algebra SL2 looks like by looking at its Lie group. And so let's recall, we want to look for the tangent space at the identity, but we can do that by looking at curves that go through the identity, stacking together their tangent vectors into a tangent space. So now let's recall that capital SL2, the group SL2, we're going to be working over the complex numbers all day. That's going to be the group of 2x2 matrices with determinant equal to 1. We could also write that as this matrix right here, ABCD, where AD minus BC is equal to 1. That's the determinant formula for a 2x2 matrix. But now what I want to do is I'll take a curve in this space. Remember that this is also like some sort of surface. So we can take a curve in this space and find its tangent vector. Then we'll package all of those together into little SL2, the Lie algebra. So let's take A of t inside of SL2C. I'll probably append the C from now on, but just right now we'll leave it for just a second. And I want it to go through the identity. So that means I need A evaluated at 0 to be the identity matrix. Let's recall that that's just the matrix read row-wise, 1, 0, 0, 1. But now I'm going to write this A of t, this matrix, well, this curve that is built out of matrices inside of SL2 with its components. So in other words, I'm going to write capital A of t as the matrix little a of t here, little b of t here, we have c of t in this entry, and then d of t in this entry. And so each of those are functions from perhaps the real numbers to the real numbers. So that's making our curve here. But now, what do we know? We know the determinant of this A of t is always equal to 1 because it's in SL2C. So that means we have the following. We have AD minus BC must be equal to 1. And I'm going to append the of t just because it'll get kind of messy. But each of these is a function of t. But next up, what I want to do is I'll take the derivative here with respect to t. Why the derivative? Because we're looking for the tangent vector at the identity. In other words, we want the tangent vector at 0. So let's do that. So taking the derivative of this with respect to t will give us a prime times d, and then plus a times d prime. That's just by the product rule in the first term. And then minus b prime times c minus b times c prime. That's got to be equal to 0 because the derivative of 1 is 0 because it's a constant. But next up, what I want to do is evaluate this at t equals 0. So let's see what I get for each of these terms when t is equal to 0. So notice if I evaluate d at 0, I'm going to get 1. And that's because we need to be able to evaluate this at 0 and get the identity matrix. So that means A of 0 is 1, B and C of 0 are 0, and D of 0 is 1. We don't know what the primes are, but we at least know what those are. So anyway, here we're going to get A prime evaluated at 0, because again, D of 0 is 1. And then for this next term, we'll get d prime evaluated at 0. And then finally, notice that these two objects right here just cancel out, or they zero out. That's because c of 0 is 0 and b of 0 is also 0. So bringing this 0 from the right-hand side of the equation down, we'll see that this is equal to 0. So in other words, we have the following setup. We have a prime of 0. So that's going to be equal to little a prime of 0, little b prime of 0, little c prime of 0, little d prime of 0. So we know that this thing is going to be in the Lie algebra of SL2 because it's a tangent vector at the identity. That's the definition of the Lie algebra. And then we also know that a prime of 0 plus d prime of 0 must be equal to 0. And in fact, that's the entire condition of the Lie algebra SL2, is that the sum of the diagonal elements must be 0. So what we could do is do a little bit of a summary here, and we'll have little SL2, and I'll put a C here, perhaps for the last time. So that's going to be a 2 by 2 matrix, A, B, C, D, such that A plus D is equal to 0. So in other words, it's a 2 by 2 matrix where the trace is 0. The trace is simply equal to the sum of the diagonal elements. And now, I'd probably be making a mistake if I didn't mention this. All of this is attached to a formula involving the determinant, the trace, the exponential of a matrix, and the logarithm of a matrix. In fact, it goes like this. The determinant of the exponential of a matrix, so I'll just write that e to the a, where a is a matrix, is going to be equal to e to the trace of that matrix. But then we can look at a logarithmic version of this and we'll see that the log of the determinant of another matrix, I'll call it B, is going to be the same thing as the trace of the logarithm applied to the matrix. So in other words, the matrix logarithm. And in fact, this formula with the matrix exponential, the matrix logarithm, as well as the determinant and the trace, gives motivation for what the actual operation on the Lie algebra will be, which we haven't talked about yet. And it actually comes from this formula that you can derive by expanding the logarithm of x times y times x inverse times y inverse. And so that's like the group commutator of matrices x and y. And so if you expand the logarithm of that, you get x times y minus y times x plus a bunch of other stuff. But if you package xy minus yx into this bracket notation, that gives you what's known as the Lie bracket. And that is the standard operation that we use on a Lie algebra. Now we can visualize that as well. So here we've got the Lie group, we've got the Lie algebra, we've got two elements of the Lie algebra. So those are tangent vectors at the identity. They're associated with two elements in the Lie group. So we'll call those little x, little y, big X, and big Y. And then we can calculate this thing, which is the group commutator of the matrices x and y. And then that's going to be pushed back up to this commutator, this Lie algebra bracket of the Lie algebra elements x and y. And this intertwining of the group operations and the Lie algebra bracket is what allows us to study the curved group via its flat shadow. In other words, the group via its Lie algebra. So looking back at our Lie algebra SL2, so those are all 2 by 2 matrices with trace 0. Now we can take an obvious basis for this algebra. So here we've got this diagonal matrix 1, 0, 0, minus 1, this upper triangular matrix, which we'll call E, which is 0, 1, 0, 0, and then this lower triangular matrix, which we'll call F, which is 0, 0, 1, 0. But then we just saw what the correct operation was on this Lie algebra. So let's look at those so-called bracket relations between these basis elements. We'll derive one carefully, and then I'll leave it to you as a bit of a homework exercise to derive the others. So we've got this HE. We can write this as HE minus EH. That's that bracket or the commutator. And so expanding that out as matrices, we've got 1, 0, 0, minus 1. That's going to be multiplied into the upper triangular matrix E. And then minus 0, 1, 0, 0 times 1, 0, 0, minus 1. Now we just have to remember how we do matrix multiplication. So let's see, for this first one, we'll have 0, 1, and then 0, 0. So notice that all the bottom row is just 0, and we get a 1 in the upper right. And then let's see, from that we need to subtract. Well, that turns into 0, minus 1, 0, 0. But now if we put that together, we're going to get 2 times 0, 1, 0, 0. I think that's pretty clear. But that's equal to 2 times E. And that gives us our bracket relation of H with E. So let's bring that up here. So we've got this bracket H with E is equal to 2 times E. And then via a really similar calculation, we have the bracket of H with F is minus 2 times F. And then the bracket of E with F will be equal to H. And that'll bring us up to the main things that we want to look in this video, and those are the representations of a Lie algebra, or in other words, using a synonym, the modules of a Lie algebra. So a vector space V is called a G module, or a representation of G, if there is some sort of bilinear action from G cross V to V. So what I really mean by that is we can take any element of the Lie algebra and it will attack any vector and give us a new vector. And it'll do that in a linear way. So it'll do that in a very nice way. And then furthermore, we have this rule that it satisfies or it preserves the bracket. So in other words, we have the bracket of xy acting on V is the same thing as x acting on y, which is acting on v, minus y, which is acting on x, which is acting on v. So notice it essentially just turns this bracket into a commutator, kind of. So let's look at what this means inside of SL2, since that's mostly what we're interested in here. So that means if we take 2 times E and we act on V, that's going to be the same thing as taking H and E and acting on V, because notice that we know the bracket of H with E is 2 times E. But then we can expand this out. That's going to be H dot E dot V, and then minus E dot H dot V. So like that. And now we'll often just abuse notation here, and we'll rewrite this as HE dot V minus EH dot V, just to keep it a little bit simpler. And now we can state our main goal, which is to classify all finite dimensional irreducible representations of SL2. And let's start with some really simple examples. Now let's start with the simplest example of a representation of SL2. It's the so-called trivial representation. So it's one-dimensional, which means it's spanned by a single vector, and then everything acts on that vector as 0. So H dot V is the same thing as E dot V, which is the same thing as F dot V, which is 0. So this is so simple that it's kind of boring. Now let's move on to the first interesting example, which is the so-called standard representation. And for the standard representation, what I mean is that we'll take two-dimensional complex vectors, and this is the standard, or sometimes the natural representation, because our SL2 are 2x2 matrices, and what do they naturally do? They multiply into two-dimensional vectors. And so we can take the maybe standard basis of C2 to be 1, 0, and 0, 1. So if we know what everything is doing to these two vectors, then we're pretty much good to go. We know everything about this representation. So let's look. So let's notice that if we were to do E times the vector 1, 0, so that's going to be the same thing as the matrix that we have for E multiplying into the vector 1, 0, but that's pretty clearly equal to the vector 0, 0. But then let's look at E acting on the vector 0, 1. So again, that's going to be the matrix for E multiplied into the vector 0, 1. But check it out, what we get there is back to the vector 1, 0. So now we know what E does to these two vectors. Now let's see what F does to these two vectors. So F multiplied into the vector 1, 0. And so we can do matrix vector multiplication here, and we'll see that we get 0, 1. And then if we look at F multiplied into the vector 0, 1, I'll let you check that you get the vector 0, 0. In other words, it zeroes the whole thing out. Now let's see what H does. So if we do H on the vector 1, 0, so recall that H was the matrix 1, 0, 0 minus 1, so we need to multiply that into the vector 1, 0. So let's observe that we just get the vector 1, 0 out again. And then if we do H onto the vector 0, 1, we will get negative what we started with. I'll let you work out the details if you want to. And so here's a picture that we'll draw based off of these actions. And what we'll see is that this picture will be like a general framework for understanding all of the representations of SL2. So let's consider this dot to be corresponding to the vector 0, 1. And let's say this dot right here is corresponding to the vector 1, 0. And let's do a little bit of color coding here. Let's say that a line segment or an arrow that is yellow corresponds to acting by E. And then maybe a line segment or an arrow that is pink corresponds to acting by F, and one that is blue is corresponding to acting by H. So let's do the actions by H first, because notice they take the vector back to themselves. So I can just put a little loop right here to show that that is the action of acting by H. And then I can put 1 and a negative 1 in here, because notice that those two vectors were H eigenvectors with eigenvalue 1 and negative 1. So now let's see what E does. Well, by this right here, notice that E takes 0, 1 to 1, 0, so that brings us up this chain right here. But then E takes this vector to 0, so we could just write that as an arrow to 0. And then, well, what about F? Well, it kind of does the opposite of E, so it'll take our vector 1, 0 back to our vector 0, 1, and then it'll take this to 0. So before we talk about a general structure, I want to work through one more example that will highlight the fact that this isn't just a cute picture, this is actually something that gets generalized. So for our next representation, we'll take the so-called adjoint representation. That is SL2 acting on itself via the bracket. So in other words, if we have x dot y, that's just simply the bracket of x and y. And so now we could just calculate some commutators and then we'll have the whole picture. So notice if we have E dot E, that's E acting on itself, that's the bracket of E with E, but that's equal to 0, just based off the fact that this bracket was the commutator. This is E times E minus E times E. But now we could look at perhaps F dot E. So that's going to be the bracket of F with E, which that's going to give us minus H. So we didn't talk about this. But if you look at xy versus yx, they differ by a sign. And so that's why we were able to only write down the bracket of EF and we got H, and then we get this one immediately. Okay, so now let's look at H dot E, and notice that that will give us the bracket of H with E, which was 2E. We saw that before. So now let's move on to perhaps acting on H. So we'll need E dot H. So notice that's going to be the bracket of E with H, but that's going to be equal to minus 2 times E, using essentially the one right above and then that symmetry. Now we'll do, what's next? F dot H. So that's going to be the bracket of F with H. That's going to give us 2F. Just by using the fact that this is going to be minus HF, but that's going to cancel the minus sign out. And then next we have H dot H, which is going to be the bracket of H with H, which is pretty clearly equal to 0 based off of what we said fairly recently. Okay, so those are the actions onto H and the actions onto E. Now what about the actions onto F? So we'll need E dot F, so that's going to be the bracket of E with F, which will give us H. We need F dot F, so that's going to be the bracket of F with F, that will give us 0. And then H dot F, that's going to be the bracket of H with F, that'll give us minus 2F. So now we know how every element of the Lie algebra acts on every basis vector of the representation. It just turns out that the basis vectors of the representation are simply the elements of the Lie algebra. That's why this all looks like we've just done the same thing over and over. Now let's draw a picture just like we had before. So I'm going to lay the basis vectors out in a certain order. So I'll put H at the end, and then we'll have, H in the middle, F on the left-hand side, and E on the right-hand side. And then we'll use our same notation. So we've got arrows that are blue are H, arrows that are yellow are E, and then arrows that are pink are F. And then we're going to have eigenvalues for all of the H's as we saw from our calculation. So notice that we had H acting on E gave us an eigenvalue of 2. That's from, let's see, H acting on E right here. H acting on H gave us an eigenvector of 0. Here we got an eigenvector of minus 2. And then furthermore, we had E brought us up the chain, and then it deposited us to 0 after the top, if you will. And then F brings us down the chain, and it deposits us at 0 after we're at the bottom, if you will. And I guess the big question here, which I've hinted at quite a bit, is now that we've seen two pictures that look similar like this, does this hint towards some sort of general structure inside of representations of SL2 as a whole? Thanks for sticking around this long in the video. If you're enjoying it, make sure and give it a thumbs up, and if you're not yet subscribed, consider subscribing, it really helps out. Okay, so here's a bit of a fact that we're not really going to prove. It's beyond the scope of what we're doing today. And that is if V is a finite dimensional representation of SL2, then the action of H is diagonalizable. But that means that V has a basis of eigenvectors of H. So if we've got a basis of eigenvectors of H, then that means that we can decompose V into pieces that all have the same eigenvalue. So in other words, we can write V as the sum over lambda of V lambda. And here, if the V lambda is not equal to just the zero vector space, then lambda is called a weight. And then just what's V lambda? Well, V lambda is equal to all V in V, where HV is equal to lambda V. In other words, it's all of the V with an eigenvector, an eigenvalue, an H eigenvalue of lambda. And this is called a weight space. So if everything in our basis is an H eigenvector, well, what about E and F? So are those going to be H eigenvectors as well, or will they be made up of linear combinations of things from different weight spaces? Well, let's see. So we can do this via a pretty simple calculation. So let's run through it. Let's do H acting on E acting on V. But then I'm going to write that as HE acting on V, kind of abusing notation a little bit. And then I'm going to take that HE and I'm going to write it as EH plus the bracket of H with E. And then that's going to all be acting on V. Now, why does that work? Well, let's recall that this HE is essentially going to be the same thing as HE minus EH. So if we put these two things together, it cancels back to what we wanted it to. But we know what the bracket of H with E is. What was it? It was 2E. So that's going to give us EH acting on V, and then plus 2E acting on V. I just wrote this H acting on V. I distributed the V through, if you will. But now H acting on V is equal to lambda times V, just based off the fact where V comes from. And so that means we can take this and we can replace it with lambda times V. But now we can factor out the numbers. Notice that lambda and 2 are just numbers. And we have lambda plus 2 times E dot V. So let's see what we have. We have H acting on this vector is the same thing as lambda plus 2 times this vector. So what that tells us is that the vector E dot V is in the lambda plus 2 eigenspace. And now we can play the same game to see where F is, or sorry, where F dot V is. So we can do H dot FV. So that's going to be the same thing as, let's see, that's going to be FH plus the bracket of H with F. And then that's acting on V. But then that's going to be equal to 2 lambda times F minus 2FV. That's because H acting on V is the same thing as multiplying by lambda, and then the bracket of H with F is minus 2F. But then we can factor stuff out here, and we have lambda minus 2 times F dot V. But that tells us that F dot V is in V lambda minus 2. So let's look at the seed of what this is telling us. So the seed that we've just seen is the following. So if we've got this vector right here that has H eigenvalue lambda, then if we push it up with E, we get an eigenvalue of lambda plus 2, and so on and so forth. If we push it back this way with F, we get an eigenvalue of lambda minus 2. But then recall that we want to look at irreducible and finite dimensional modules or representations. Irreducible just means that we can't break them into smaller pieces. And well, finite dimensional just to keep everything a little simpler. And so that means that the dimension of any of these V mu has to be 0 or 1. So if it's two-dimensional, then we'll have these two disjoint lines here, and it'll no longer be irreducible. And then the fact that it's finite dimensional means that there's got to be a vector v0 so that if we hit it with e, we get 0. Because if there's no such vector, then this chain will just go infinitely to the right. And so what we'll do is we'll call that vector v sub 0, and we'll call the weight attached to that vector lambda the highest weight. And the vector will be called the highest weight vector. So that means we've got a highest weight for this thing of lambda, and the vector, the highest weight vector, is v0. So just as a bit of a summary, we've got v0 in v lambda, and then if we go up that way with e, we just get 0. And then v1 will be f times v0. And that'll be in v lambda minus 2. v2 will be f squared v0. That'll be in v lambda minus 4. All the way down, vn will be f applied n times to v0. And that'll be in v lambda minus 2n. And then again, since this is finite dimensional, we need to hit a place where if we apply f enough, we get 0. But that's just working with f descending us down the chain. And what happens if we ascend the chain with e? Well, notice that e applied to vk will be a multiple of vk plus 1 because that moves us up one weight. So now the question is, well, what's that multiple? So if we call that multiple ck, then maybe we could find some sort of formula that will define what ck is. Well, notice that we know that e times v0 is 0, but that tells us that c0 must be equal to 0, because notice that we've got nothing over there on the right-hand side. But then we can also look at this equation, which will be very telling, and that is if we take ck plus 1 times vk, and if we subtract ck times vk and expand those out as follows. So this is going to be EF times VK. So let's talk our way through that. So F times VK is going to be VK plus 1 by what we have over here. And then if we apply E to VK plus 1, we'll get back to CK plus 1 VK by this formula right here. And then from that, we will subtract FE VK. And that's because EVK will be CK VK minus 1, and then F brings that back up to VK. But let's observe that that's simply the bracket of E with F acting on VK. In other words, that's H acting on VK. But notice that H acting on VK is lambda minus 2K times VK, which we can see from our chart right here. And now what we can do is extract the coefficients of VK from both sides of this equation and move some things around, and we'll see that CK plus 1 is equal to CK plus lambda minus 2 times K. And then we've got this seed of C0 equals 0. It gives us this nice recursion for our CKs. And now that we have this recursion, let's see if we can guess at the closed form for one of these CKs. And I think we can do that just by looking at a chart. So let's make our chart. We've got K, and then we have C sub K. And we'll do this for a couple of entries. And I think after a couple of entries, we'll see what we have. So C of 0 is equal to 0. That was our seed. And then C sub 1, well, that's going to be C0 plus lambda minus 0. That's simply going to be lambda. And then for C sub 2, we'll have lambda plus lambda minus 2. We can write that as 2 times lambda minus 1. And then let's see, for C sub 3, we'll have 2 lambda minus 1 plus lambda minus, well, that's going to be minus 4. So putting all that together, we're going to have 3 times lambda minus 2. But I think you can maybe see what pattern is being constructed here, and that is for the kth term, we will have k times lambda minus k plus 1. Now, that may not seem super helpful, but that's actually going to allow us to determine that lambda can only take certain values. So let's see how that calculation goes. So far what we saw is if we have an irreducible finite dimensional representation, then it has to have this basis v0, v1 up to vn, where v0 is our highest weight vector, And then vk plus 1 was f applied to vk, so it's this iterative process. And then f applied to vn was 0, whereas e applied to v0 was 0. And then finally, we had this e applied to vk as k times lambda minus k plus 1 times vk minus 1. Okay, good. But now I said that we could get some restrictions on what what lambda has to be. So let's see how we can do that. So it's all going to be built off of this thing that we already have on the board. We have f applied to vn is equal to 0. But if we were to call f applied to vn plus 1, that means that we need vn plus 1 to be 0. But then we know that e applied to vn plus 1 has got to be equal to cn plus 1 times vn, just based off of this rule right here, where remember that this was the ck number that we had before. But then this vn plus 1 vector is the 0 vector, so we need this also to be the 0 vector. But vn is not the 0 vector, which means we need cn plus 1 to be equal to 0. But then plugging n plus 1 into here, that's going to give this equation, n plus 1 times lambda minus n has to be equal to 0, which means lambda must be equal to n. And that's actually a really big takeaway, is if you've got an irreducible representation of SL2 that's finite dimensional, and let's say it has n plus 1 dimensions, then this highest weight lambda has to be equal to n, one less than the dimension that we're working with. So now let's look at a nice visualization of all of this in action. So we can start with the trivial representation and observe that this satisfies this picture. So h goes back to the original vector with the eigenvalue of 0, and then e and f turn the vector into 0 as well. And then we also already saw the standard representation, the two-dimensional representation, had this picture. And the adjoint representation also had this picture. So these two representations were what motivated us to look down this road in the first place. But it turns out that it continues on. So we've got a four-dimensional representation that is built via this picture, and then 5, 6, 7, 8, 9, 10-dimensional representations that build this picture. In fact, this turns into a complete classification of all finite dimensional irreducible representations of SL2. So we won't check that this is a complete classification, carefully at least, but this classifies all of these representations. So before we do our final task at looking at a realization of these representations, I'd like to tell you about my second channel, Math Major, which has full lecture courses and mostly upper division math classes. And in fact, I keep that channel ad-free thanks to my support on Patreon and via channel memberships. If you'd like to contribute to helping me keeping that ad-free, consider becoming a patron or joining the channel, but there's no pressure. Okay, so now that we've classified all of these irreducible finite dimensional representations, let's look at a nice realization of them. So let's take Wn to be the span of all degree n, well, homogeneous degree n polynomials in the variables x and y. And so we can write down a pretty simple basis like this. It'll be x to the n minus 1 times y. The next one will be x to the n minus 2 times y squared, going all the way up to y to the n. And then h will act as x times the derivative with respect to x minus y times the derivative with respect to y. And then e will act as x and then the partial with respect to y. And f will be y and then the partial with respect to x. And so we won't check all of the details to show this is a representation, but we will do a sample calculation. So let's see what happens when you do the bracket of e with f acting on a test function at a. So that means we're going to have ef acting on a minus fe acting on a. But notice that f acting on a is simply going to be equal to y and then the partial of a with respect to x. So I'll just write that as a sub x. And then here we'll have f, and then e acting on a will be x, and then the partial of a with respect to y. But now let's act with the remaining things. So e means we need to take the partial with respect to y. We've got to use the product rule here. So that's going to give us x times, and then we'll have a sub x plus y, and then a sub xy. That's the second partial. Then I just left that x out front. And then next we'll have minus, and then we'll have a sub y, and then plus x times this partial xy. That's just by taking the derivative again with the product rule. But notice that we've got some terms that repeat and thus cancel. This will cancel with this. And in the end, we're going to be left with x, and then the partial of a with respect to x minus y, and the partial of a with respect to y. In other words, that's just h acting on a, because h is exactly that kind of action here. Okay, so this EFA being the same thing as HA is exactly the kind of thing that you need to check that this is a representation in the first place. And then you can do some other sample calculations to convince yourself that this is a realization of the same representation that we just hinted at. Let's say we do h acting on x to the a, y to the b. Well, just by taking derivatives, it's pretty easy to see that this is going to be a minus b times x to the a, y to the b. So that means that this x to the a, y to the b is an eigenvector of h. And then you can look at e acting on this same monomial, and you'll see that this is going to be b x to the a plus 1, y to the b minus 1, and then f acting on this same monomial will give us a x to the a minus 1, y to the b plus 1. So that gives us a hint at this chain forming. So let's see, we've got x to the a, y to the b in the middle. We'll put that thing in the middle. And then over here we'll have x to the a plus 1, y to the b minus 1. And then over here we'll have x to the a minus 1, y to the b. And we see that each of these is an eigenvector of our action by h. And then we've laid this out so that E is pushing us up the chain, and then F is pushing us down the chain. Now, if you check, you'll see that E and F don't act with the same scalars as they did before, but you can re-index or maybe re-normalize the basis here to have it act with exactly the same scalars. Okay, so, well, that's about all we needed to do today, but before we end, I'd like to point out that all of the semi-simple Lie algebras, so that would be like SLN, we looked at SL2 today, SON and SP2N, as well as the exceptional ones, have copies of SL2 inside of them, which gives rise to these chains of representations in their representations. And those chains allow you to decompose the representations of those bigger Lie algebras so that you can understand them in terms of this representation of this simplest one, this SL2, which is why understanding this maybe seed case is the most important thing to understanding the representations of Lie algebras as a whole. And that's a good place to stop.